A much older neuroimaging technique, you wouldn't normally think of it as an imaging technique, but it is the electroencephalogram, or reading brain waves. The term brain waves is perhaps a little bit misleading here. This is recorded from the scalp using a headpiece like you see there. And from each electrode we get a trace, a recording, which we can interpret perhaps as a signal, but we'll see there's difficulties here. It is entirely non-invasive, harmless. This does no damage to anybody, so we're happy to do this with children. It takes a while to put on the cap and make sure all the electrodes are sitting well. These days we've got very good gels that make sure you don't have to shave your head for this. And what you record varies sensitively moment by moment, so it has extraordinarily good time resolution. You can note changes that happen in less than 1,000th of a second. Compare that to fMRI, where we had to wait 5 seconds for a scan, so completely different. But where MRI and fMRI were very good at localizing things in space, EEG is terrible at that. There's very little to go on to figure out where what you're recording is coming from. This is the oldest method, and the idea that one might take a reading from an electrode on the scalp was first introduced by Hans Berger in 1924, and there's one of the original recordings that Hans Berger made. The recording from the electrode is the top of the two lines, and the lower line is a reference 50 Hertz alternating current. Looking at that, it's kind of hard to figure out anything, isn't it? This does not give us a direct line to anybody's mind, thoughts, feelings, contents of consciousness, or anything else. What we have here is a puzzle. It's complex. If I call it a signal, that says more about my attitude with respect to it than about the coherent generation of it. Because when you record from an electrode on the scalp, you're recording diffuse variation in electrical conductance. There is electrical underlying activity in the brain. The brain is not just an electrical signaling system, but an electrochemical system. But as a result, there's some fluctuation in electrical activity. But that has to pass through multiple layers of connective tissue, fluid, bone, and skin. So that by the time I pick it up here, it's not clearly directly relevant, coming from any specific point in the brain. Furthermore, the electrical activity that I do happen to measure is from those parts of the neocortex that by chance, because the neocortex is folded, some parts necessarily must lie closer to the skull than others. Imagine you take a sheet of paper, crumple it up and stick it into a tennis ball. Some parts of the sheet of paper are close to the surface and others are not. Now imagine you had a nice drawing of a clown on that sheet of paper. There's no reason for the clown to be well represented if all you had access to was those parts of the paper that lie close to the surface. So this is a real problem. The signal is not directly interpretable, but we can do a lot better than nothing with it. So from one electrode we might get that kind of complex signal you see there on the screen. And in a contemporary setup we might have 128 of these electrodes. That helps in localizing things a little bit. One way to treat this is to break it down into its component frequencies. Just like a sound wave, any complex waveform can be broken down as if it was the sum of simpler frequencies, low frequency to high frequency, mixed together at different amplitudes. You're familiar with this from a stereo system where you can selectively increase the volume of the bass or the treble. That's just like two frequency ranges. Here we can select our frequency range and look at the amplitude of this through that narrow lens. That's what's often done, and when we use particular frequency ranges, they have Greek letters associated with them, alpha, beta, gamma, delta, and the Greek letters bear purely circumstantial relation to the frequency ranges. They were not named in historical sequence and they don't follow alphabetical order, so they're just random names. So considering this one, if we break it down into 4 distinct frequency ranges, What I'm showing there is one low frequency range called the delta range. And we find greater power here. For example, if you take an EEG of a child than of an adult. There's greater power here in some kind of pathologies than in a normally functioning brain. And there are some sleep states in which there's elevated power in this frequency range. If we move up to the next highest frequency range, you can see the squiggles are getting a little bit more frequent here. This is known as the theta range. And we find increased power in the theta range compared to the others when people are drowsy, in light sleep, or in a state of hypnosis. So these kinds of analyses are quite good at differentiating between various states of consciousness. The beta range, now you can see this signal is oscillating much faster. This gets more power when you are actively thinking about things, planning, reasoning, solving puzzles and the like, actively concentrating or reading. And the highest one there, the gamma, is associated likewise with highly intellectual activities, problem solving. As you can see, it's a bit messy. What we have is something we can look at and we can ask, does this co-vary with anything? So it's an extremely noisy beast. Calling it a signal is almost overblown. And it's not interpretable as it stands. But these characteristic changes in the relative amplitude at different frequencies provide us with a very, very useful tool for distinguishing, for example, different states of consciousness. And that turns out to be extremely important. For example, if you want to evaluate how someone is doing if they're in a coma. So experience of working with these is useful for in a clinical setting, and it provides a difficult tool to wield in experiments. Experimenters like something that's clearer, and sometimes in experimentation it's difficult to combine the messiness of the real world with the constraints of the experimental laboratory. One way this is attempted in EEG work is using a technique known as the event-related potential. What happens here is that something is done to somebody. So supposing you're just sitting there and someone comes along and taps on the head. And we record an EEG and we know where the tap occurred. And then we do it again. And we do it again. You're going to get very sick of this after a while. We don't actually tap them on the head, but we might show them an image or play a sound at them, use what's called a stimulus. Don't like that term, but there you go. And after doing the same thing several hundred times, if we average those noisy signals, then the noise will be washed out, and what we'll have left is something. Well, it's something that looks like the graph you see on the lower right there. This is an event-related potential. That is what was common between those 150 taps on the head. And you can see there's a characteristic shape to it. When the graph goes down, it's called a positivity. When it goes up, it's called a negativity. That's weird. Doesn't matter. But how do you interpret something like this? It's certainly not capturing what is usually claimed, which is the brain's response to, for example, being tapped on the head. Well, it's not capturing the person's response to being tapped on the head, because if I do something to you once, you might put up with it. If I do it twice, you might object. If I do it 150 times, your response to the 150th one will be very different from your response to the first one. So in that sense, all that variation is wiped out here. And something is left which is invariant over all those repetitions. So these are very hard signals to work with, hard to collect, and much harder to interpret. There are those who believe they can do that. And so this is one particular corner of the world of EEG that lends itself to experimental work. So in all EEG work, we have to be humble. The signal-to-noise ratio, if this is a signal, is very small. It's difficult to detect anything other than randomness, but that doesn't mean that they're not useful. You get stronger signals when you average across many trials, but this averaging always brings the problem with it that the ongoing sense-making activity of the subject, which is surely what we might call consciousness, is not recorded. Something else is. The design of experiments that make use of these is very complex, so there's lots of questions you can't ask. This would be true for all our methodologies. A particular problem with EEG is it's very difficult to say where in the brain your recording originated. Spatial localization is difficult, but its temporal resolution is very, very good, so we can say with a great deal of certainty when something happened. And there's that problem of the sheet of paper inside a tennis ball. We're recording nothing from most of the brain. All the deep brain structures and most of the neocortex is not recorded here at all. Rather, the signal that we get comes from those parts of the brain which by chance happen to lie near the skull. You can see these tools aren't easy to work with, but they're all we got.